So this unit just consists of a couple different things. So we started out with vectors, and then we worked on parametric equations. Now we're going to switch over to polar coordinates. Okay, so things are going to kind of coincide a little bit, but we're kind of shifting gears. So guys, everything you've been used to is rectangular. So when you graph something, you use an ordered pair and you graph the point. So if I give you the point 2, 3, you're going to go to the right 2 spaces, up 3 spaces. And that is the only point that you can put on the graph. With polar coordinates, and this is what a polar graph looks like. I'm going to switch the slide here. But for a polar graph, it's going to look like this. Instead of being called the origin, this is called the pole in the middle. If you notice, it goes just by your unit circle. So here we have 0, pi over 6. Sometimes they put the middle line on here, sometimes they don't. But if they would have had the middle line here, it would have been your pi over 4 and then pi over 3. So these are the radian measures that come from your unit circle. Okay. When you graph a point, so for a polar coordinate, so a lot of times it has a P just to stand for the point beside of it, but it's going to be r theta. So r stands for the radius, and then theta stands for the angle, and this could be in radians or it could be in degrees. Most of the time radians, but radians or degrees, just like you use on your unit circle. Some other things, this is called, instead of your x-axis, this is called your polar axis here. And then, like I said, your pole is your origin. Just to relate this, a rectangular coordinate that you've been graphing since way back, that is xy. X tells you you're going to the left or the right, y tells you going up or down. And like I said, this point is unique. You can only graph this in one place. So unique, only graph at one place. Whereas you're going to see with polar, radius and angle could happen at a bunch of different places on the graph. Okay, on this polar graph. So moving on to the next slide, a couple more details. So like we just said, polar coordinates for a point are in the form r theta. R is the distance from the origin or the pole, so your radius, and theta is your angle from your polar axis. And remember, the polar axis is where you start here at 0. Theta is positive when you go counterclockwise. So think about the unit circle. If you were to go counterclockwise, that's going in the right direction, so it's positive. Your angle is negative if you were to move clockwise, so backwards. With a rectangular coordinate, xy is a unique point. So what I was saying here, polar coordinates are not going to be unique. You can graph a certain point at different places on the graph, or you can write them in a different way. The pole can be written as lots of different ways. So the pole just has to be 0, and then this theta could be any angle. The reason is, if the radius is 0, you're not going to move at all, so you would be at the pole no matter what the angle is. Okay. Just want to go back and reiterate, because I think I said something a little bit incorrectly. But for your rectangular coordinate, when you graph xy, this is the only way you can write the point, and it will get you to one unique location. When you have polar coordinates, it may be at one place on that graph, but you can write it in different ways. It will not be a unique ordered pair that you can only use once. Okay, so we'll see that. Alright, so we're going to start by just plotting these points, and I am going to use this graph. If you don't have your own graph, you can just draw like a circle and you can just sketch from there. So we're going to plot the point 2, 5 pi over 4. Let me just write a little information on here. Okay, 2, 5 pi over 4. So the 2 stands for your radius, and the 5 pi over 4 is your angle. When you start graphing these, you are going to always go to the angle part first. Okay, so you want to find 5 pi over 4. Just think about on your unit circle. So here's 5 pi over 4, and the radius is 2. So you're going to go over here to 5 pi over 4. You're going to start from the pole, which is the center, and you're going to count 2 spaces. And so right here is where your point A would be. Okay. I'm going to put this color right here so we can match. But this would be your point A, 5 pi over 4, and it's 2 spaces for the radius. So if you look at point B, so 1 is our radius, negative 7 pi over 6 is our angle. So you always start with the angle. Now negative 7 pi over 6 is not on your unit circle, but we can do those coterminal angles and make it on our unit circle. So remember, if you want to do coterminal angles, you're going to add a whole circle because this one's negative. So if we make these have the same denominator of 6, I would write this as 12 pi. So this is 5 pi over 6. So B can also be written as 1 5 pi over 6. So this is where that not being a unique point came in place. These two mean the exact same thing. They're going to graph the exact same point on the unit circle. So we're going to go to our angle part first. So we're going to find 5 pi over 6. Let me change colors. So we're going to do orange here. So we're going to find 5 pi over 6, which is here. And it says the radius is 1. So go down here, go from the pole and go to 1. And so this orange spot right here is where your point B would be. Okay, and then for point C, so my angle here is 4 pi over 3, which is on the unit circle. So let's do this one green. So if we find 4 pi over 3, which is here, I'm going to go ahead and move to the center. Now, this says negative 4. So if it said positive 4, let's think about what that would be. So 4 pi over 3, if it said 4, we would go count 1, 2, 3, 4, and this is where the point would be. Because it's negative, that means you're going to go backwards. So, you're going to go to 4 pi over 3. You're going to follow that 4 pi over 3, which you see how it connects to pi over 3. So you're actually going to move 4 spaces on pi over 3. So this is where the point would be located. So think about that. This is the same thing as saying positive 4 pi over 3. So look what I mean here. Now because we went backwards, we actually landed on pi over 3. Well, we went up 4. So this is the same point. These mean the exact same thing here. So with polar coordinates, there are multiple ways to rewrite every point. Because think about coterminal angles. There are an infinite number of coterminal angles, so you could write this. Alright, so if we look at point D, we have 5 pi. So, let's do this one, this lime green. So for 5 pi, we're going to find pi, which is here. We're going to go to the center, and then we want to move 5 spaces. So 1, 2, 3, 4, 5. And that's where our point D would be. And then for point E, just make it black. If you find pi over 3, which is here, now because it says this negative 2, we're going to have to move backwards. So pi over 3 actually connects to 4 pi over 3. So you're actually going to be going 2 spaces backwards. So looking at E, another way we could write that same point would be going 2 spaces on 4 pi over 3 instead of going backwards on regular pi over 3. So that's how you would graph those. Okay, so for the next part, we want to write 2 other names for 3 2 pi over 3. So very similar to what we were just doing. So for the point that we're working with here, 3 2 pi over 3. So let's go ahead and graph this point. So if we find 2 pi over 3, which is here, go down to our pole and then count 1, 2, 3 spaces. So this is the point that we're working with here. Yes, got a little carried away. But right here, 1, 2, 3 spaces up on 2 pi over 3. Okay, so writing different names. It says to write 2 other names. So first name, if you look at 2 pi over 3, it connects with 5 pi over 3. Okay, so 2 pi over 3 conflicts with 5 pi over 3. So if we wanted to use 5 pi over 3, if I told you to graph on 5 pi over 3 and you had to move 3 spaces, you would technically be moving backwards. So this right here is another point. This would be considered our backwards point. Okay, I want to show you how you get that algebraically in case you do not have a graph. So do you see how 2 pi over 3 and 5 pi over 3 are half a circle apart? Well, because they're half a circle apart, in radians that would be they are pi apart. So if you were to take 2 pi over 3 and you were to add pi to that, so if you make these have the same denominators, that's where that 5 pi over 3 comes from. So whenever you're doing the backwards one, if for some reason you don't have a graph or don't have your unit circle, you can always just add pi or subtract pi, and that'll get you on the other place in the unit circle. So here's one answer. That's the backwards answer. Then another answer could just be any coterminal angle. So if we take our original point here, if we want to find another coterminal angle for 2 pi over 3, you could just add or you could subtract the circle. So if I make these have the same denominators of 3, this would be at 8 pi over 3. So another option for our point could be the point 3, 8 pi over 3. Okay, 8 pi over 3 is the same thing as 2 pi over 3, and you're still moving up 3 spaces. There are so many other points that you could write. You could also take your backwards one, and if you wanted to add your 2 pi to the 5 pi over 3, you could get another one. You could have subtracted instead of added 2 pi. There are tons of different answers that you could get. So then on the last part it says write all the different solutions. So remember I told you there's an infinite amount. So if you want to write all different solutions, you really need to write 2 different answers. So first you're going to take your original point, 3, 2 pi over 3, and we can add or subtract an entire unit circle. Remember we write that as 2 pi n. Remember n is just this integer 0, 1, 2, 3, a number like that. So that's one answer you need to write. Then you also need to write the backwards answer. So we know the backwards answer is negative 3, 5 pi over 3. And same thing here. This 5 pi over 3, we can add or subtract an entire circle over and over and over and over again. So this right here would represent all the different possibilities of ways you could write that same point. So we're talking about this exact same point on the graph, but these are all the different ways that you could write.